Hey everybody, Miss C here, and today's video we're going to talk about significant figures, affectionately known as sig figs. So sig figs, or significant figures, is how we know where to round our answers whenever we do a calculation. So significant figures are found in measurements. In chemistry, all the data that we take is a measurement of sorts, whether we're measuring the length or the volume of something, the speed of something, how many moles we have, volume, particles, right? We're always looking at a quantity that is a measurement. And so because of that, we need to round our answers to appropriate number of digits so that we can show how precise our answers are. So significant figures in measurements have to include all the digits that are known plus an estimated digit. So we always say what we know for certain, and then we are allowed, because we have brains, to estimate one digit past what we know. So for example, if I were looking at this ruler here, I can see that I'm going up 1, 2, 3 with my big numbers. And then in between, there are 10 little decimal places. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. So it's going up by 0.1 every time. So because I'm going up by 0.1, and this is the same on your rulers, that means that my known value is 0.1. which means I need to estimate some number past it. So in this case, I can see for certain that my line with the hash marks is at least 2.12345, but it's not quite to the 0.6. So I know for certain that it's 2.5. I know that. And then I can say, well, it looks like it's kind of in between, maybe a little bit closer to the 6 than the 5. So I might say it's a little more than half, so 2.56. Now, if the person next to you was measuring this, they might have said 2.55, or somebody might have said 2.54. Well, we would all be consistent in the 2.5 region, but we would vary a little bit on our estimate. This tells us that we know for a fact it's 2.5 and that we have a little bit of uncertainty in our last digit of the 6 in my case. So we need to be able to look at a number and identify which ones in that number are significant or that they show precision, and which ones are not, they're just placeholders. And any number that is a non-zero number is significant. It's our zeros that really trip us up. So we need to talk about zeros. Any zero to the left of a number, so in front of a non-zero digit, is never significant. So for example, if I have 0.0063, these zeros, they're simply a placeholder to make my number small. They're put in there, and I can keep adding zeros beforehand. I could put zeros in front here. They're just placeholders. They're not changing the value of my number. Zeros between non-zero digits are always significant. So that means that this zero here is there because I have exactly 2,083 of something. Okay, that is there because it is part of the number. So they're always significant. So that means that if I wanted to know the number of sig figs that I have in this number I have 2 significant figures. Whereas in this number, all of my non-zero numbers count, as does a 0 because it's between. I have 4 sig figs in this number. All 4 of these numbers are significant. Zeros to the right of a non-zero number, but after a decimal place, or when there's a decimal place present, are always significant. So that means this decimal place tells us I know exactly to the 10th, 100th place that I have that precision. So in this case here, there are 4 sig figs. Because these are not placeholders, they're telling us how precise our measurement is. However, if we don't have a decimal point here, these numbers are simply placeholders. So zeros after non-zero numbers with no decimal point are never significant. This is because they are simply a placeholder to make the number big. I continue to add zeros, and that would therefore make my number bigger and bigger. So this number here, just my non-zero numbers of the 1 and the 6 count in terms of significant figures. So in here I have 2 sig figs. If I had the number 16,000.0, now I would change this to saying I know with precision to the 10th place, and I would have 1, 2, 3, 4, 5, 6 sig figs. Okay. One way to remember this is we can remember the phrase no, N period O. This stands for beginning zeros. So the zeros at the beginning are never significant. Ending zeros are only significant if there's a decimal point. So we include the decimal point here, the period. We're saying beginning ones are never, ending ones are only if there's a decimal present. So what about calculations? We're going to use significant figures in calculations. Anytime we do any sort of math, we're going to round our final answer to the correct number of significant figures. You're going to get lots of practice at it. I don't expect you to be perfect right away, but we'll get there by the end of the quarter. So a calculated answer cannot be more precise than the least precise measurement from which it was calculated. So if I was using a shoestring to measure the length of my desk compared to a ruler, I could only measure in quantities of shoestrings, maybe a half of a shoestring. But if I had a ruler, I could measure to a centimeters or millimeters. I could have much more precise measurements. So addition and subtraction have a different rule than multiplication and division because it can't be easy. So addition and subtraction, the calculation should be rounded to the same number of decimal places as the measurement with the least number of decimal places, so the least precise measurement. We can write them this way. Sometimes it's easier to stack them vertically because you can more easily see the decimal places. So I'm going to go ahead and do that just to show you the decimal places. So I have 41.3, then I have 0.398, and 11.24. I can see that my least common number of decimal places is here in the tenths place. This number only goes to the tenth. This one goes to the thousandths. This one to the hundredths. My common decimal place, or the number with the least precision, is this number here because it's only precise to the tenths place. So when I add these up, I can see that, so I have 41.3 plus 0.398 plus 11.24. I get 52.938, but I can only be precise to my tenths place. So that means I must round. The number after my last known digit is less than 5, so I'm going to round down to 9. So that means my final answer is 52.9, and there's no units on this, so I can just leave it as is. My next question says to find the total mass of 3 chocolate bars with a mass of 2.4 grams, 2.32 grams, and 1.743 grams. Here, I know to the hundredths place, here to the hundredths place, here to the thousandths. My least precise measurement is to the hundredths place, so that's what I'm going to round my answer to. So when we add these together, 2.4 plus 2.32, and this is 2.40. I should have added that in. 2.32 and 1.743, and we get an answer of 6.463. Remember that this 0, because of the decimal point, makes it significant. I can round my answer to the hundredths place, so my 6. Number after it is less than 5, so I round down to 6 as opposed to up to 7. So my answer is 6.46, and we get units here of grams. Excuse me. Finally, multiplication and division. We use multiplication and division more than any other math process in chemistry. And so this is the one you'll end up being most familiar with. Calculations will be rounded to the same number of significant figures as the measurement with the least number of sig figs. So we always have to look to see how many sig figs do we have in each of our numbers, and then we'll round our final answer accordingly. So in my first problem, 21.34, this gives me 4 significant figures, all non-zero numbers. My second number, 5.43, this 0 comes after a decimal place, so this has 3 sig figs. 3 is less than 4, so my final answer can only have 3 sig figs. So when I multiply these together, I have 21.34 times 5.40, and I get an answer of 115.236. My total number of sig figs I can have when I'm done is 3. So that's starting from the left, 1, 2, 3. So 5 is my last number I can have. The number after it is less than 5, so I round down. So my final answer is 115, and no units are given. In our last example problem, we're asked to calculate the volume of a box whose sides are 3.4 meters, 2.04 meters, and 4.7 meters. Remember that volume is length times width times height. So I'm going to have 3.4 meters times 2.04 meters times 4.7 meters. Looking at my numbers, here I have 2 sig figs. Here I have a sandwich zero in between, that's 3 sig figs, that one counts. And here I have 2 sig figs. So my final answer, I can only have 2 significant figures. When I plug these into my calculator, 3.4 times 2.04 times 4.7, I get a final answer of 32.5992. Now I can only have 2 sig figs, starting from the left, 3 and 2. The number after my 2 is a 5, so that means that I round up to 33, not down to 32. So my final answer is 33. I have meters times meters times meters. So meters by meters by meters, meters squared, meters cubed. So my final answer is 33 meters cubed. And that is what you need to know on significant figures and calculations.